So in this video, we will see a light historical background and understanding of the concept of linear regression analysis. So linear regression started in the 1800s with a guy named Francis Galton in the UK. You might have heard of his more famous cousin named Charles Darwin. So Galton was studying the relationship between parents and their children. In particular, he investigated the relationship between the heights of fathers and their sons. He discovered that a man's son tended to be roughly as tall as his father. However, his breakthrough was that the son's height tended to be closer to the overall average height of all the sons under study or the general population. That is, a tall man's son will tend to be taller than the average population, but not necessarily as tall as the father himself. Similarly, a shorter man's son will likely be shorter but more closer to the overall average height. Let's see this with an example of Shaquille O'Neal, who is a famous former NBA player. Shaquille is really tall, tall as in 7 foot 1 inch or 2.2 meters. Now if Shaquille had a son, chances were he would be pretty tall too. However, Shaquille is such an anomaly that there is also a very good chance that his son will not be as tall as Shaquille himself. Turns out that was the case. Shaquille's son is pretty tall, he is 6 foot 7 inch, but he is not nearly as tall as his father. Galton called this phenomenon regression, as in a father's son's height tends to regress or drift towards the mean height or the average height of the overall population. To understand this, let's take the simplest possible example, that is calculating a regression with only two data points. Now here, as there were only 2 points, the straight line would pass over those 2 points. All we are trying to do when we calculate our regression line is to draw a line that's as close to every dot as possible. Now if there were more than 2 points, and imagine them not to be collinear points, then a straight line can't pass through all of them. So we would want that line to be as close to the points as possible. For classic linear regression or least squares method, you only measure the closeness in the up and down direction. So wouldn't it be great if we could apply this same concept to a graph with more than just two data points? So imagine all of these points here. In this graph here, on the x-axis we have father's height, and on the y-axis we have son's height, and we have a lot of data points here. So by doing so, by applying a line to more than two data points, we could take multiple men's and their son's height and do things like tell a man how tall we expect his son to be even before his son is born. And congratulations, you have become a seer. But more seriously, the height that we predict is not necessarily going to be true. But the keyword here is we expect. And this is the idea behind supervised learning, that we are going to have a bunch of labeled data points using which we will create a model to predict a variable given other variables. Our goal with linear regression is to minimize the vertical distance between all the data points and our line. So in determining the best line, we are attempting to minimize the distance between all the points and their distance to our line. Now there are a lot of different ways to minimize this. Methods like sum of squared errors or sum of absolute errors and few other methods. Absolute error would basically be this individual data points minus this predicted line, and some of these would be positive, some of these would be negative. So that they don't cancel out each other, we have absolute error. We will take the absolute value of each of those and add those up. In sum of squared errors, we'll find the error, that is the y value of the actual data points minus the predicted y value, and we will square all of those, and we will square and sum all of those. Now in this method, it will punish the extreme large values and will give more importance to the smaller values. So there are these different methods, but all of these methods have a general goal of minimizing the distance between the uh, actual data points and the predicted values. So for example, one of the most popular methods is the least square methods. So here, let's imagine we have some data points in blue here along the x and y axis. Now imagine we want to fit a linear regression line through this. But the question is, how do we decide which line is the best fitting one? Because we have this line going through the data points here, but this line could very well have been above all of these blue points or below all of these blue points or passing through the points, something like this. So which of this is the best fitting lines? So for that we will use the least squares method, which is fitted by minimizing the sum of square of the residuals. The residuals of an observation is the difference between the observation, which is the y value, and the fitted line. So these blue dots are the observation, black line is the fitted line, and these red lines are the residuals. So it is the distance between the actual y value to this predicted y value. And this distance, this is the residual for this data point. Similarly, we have residual for this data point, residual for this data point. So we'll find this residuals, square everything up and sum that, and whichever line, whether this black line or this line or this line, whichever line has the least value, that will be selected as the best fitted line. Now this is our regression model, and using this we can predict the corresponding y value for any given x value. This was a simple explanation of the linear regression model. So that's all for now. Thanks for your time.